So we've just established the product to sum identities, all right? This is one of them. A product becomes a sum, and there were 4 of them. This is one of them. I changed the variables for the angles from A to B to alpha and beta, okay, the Greek letters, alpha and beta. And that's just because I want to establish A and B separately here in a moment. What we're going to do is we're going to use this formula to derive another formula called a sum to product formula. Instead of a product to sum, it's a sum to product, so it's going to go the other way. To do that, I'm going to relabel my angles first. So I'm going to take this alpha plus beta, I'm going to call it A, and alpha minus beta, I'm going to call it B. These are going to be my 2 angles. All right. Now from these 2 angles, A and B, I can write a couple of equations. First of all, I could just write out alpha plus beta equals A and alpha minus beta equals B, right? I have those 2 equations. If I were to add those 2 equations together, yeah, I should do that instead. Let's do that. Let's write it vertically. Alpha minus beta equals B. If I were to add those 2 equations together, term by term, that would give me 2 alpha, alpha plus alpha. Beta minus beta is 0, those drop off, and that equals A plus B, right? That's the sum of the 2 equations. And then that means that alpha must equal A plus B over 2. It ends up being the average of A and B. All right. I can establish another equation by looking at the difference between the 2 equations. So if I did alpha plus beta equals A, and alpha minus beta equals B, and if I subtract them, well, that subtraction distributes to every term, right? I'm subtracting every term. So that's like doing a minus alpha plus beta minus B. Everything gets subtracted, and then you combine your terms. Well, the alphas drop out. You get 2 beta equals A minus B by subtracting, okay? And then again, if I solve that for beta, I could divide out the 2 on both sides. I get beta equals A minus B over 2, all right? So I've established an expression for alpha and beta. So now if I go back to this original equation, I can replace alpha here. This alpha becomes A plus B over 2, and this beta becomes A minus B over 2, right? So I'm just doing a variable swap essentially for the angles. And so then I could rewrite this entire equation as the sine of A plus B over 2 times the cosine of A minus B over 2 is equal to 1/2 the quantity of the sine of A plus the sine of B. All right, so I've changed the variables a little bit. Now, if I multiply both sides by this 2 to get rid of the fraction, I would end up with 2 times the sine of A plus B over 2 times the cosine of A minus B over 2 is equal to the sine of A plus the sine of B. All right? So what we've done is we've now gone from a product converting to a sum. Now I have a sum that I can convert into a product. Okay? A sum to a product. And just as an example real quick, if I wanted to find, let's say I wanted the sine of 10 degrees plus the sine of 20 degrees, if I didn't know either of those individually, well, I could find that sum using this formula. I could convert that to 2 times the sine of, well, then I do a plus b over 2. Well, 10 plus 20 is 30. 30 over 2 is 15, so it'd be a 15-degree angle, times the cosine of a minus b over 2. Well, 10 minus 20 is negative 10, divided by 2 is negative 5. So it would be a negative 5-degree angle. Now, it may be the case that this isn't any more easy to evaluate than the original. Like in this case, sine of 10, sine of 20, sine of 15, cosine negative 5. None of them are really easy to solve. I just threw some numbers in there. But it could be the case that they are, that one side is easier to evaluate than the other because they represent maybe angles in our special triangles or something like that. Okay, so we can establish some nice relationships here. We can also use these formulas to derive more identities. Okay, so just some kind of neat ideas. So I can change a sum into a product now using this identity. This is a sum to product identity. Okay, and there are 4 of them, right? So I've established one of them right here, but there are 4 of them, and they each come from one of the product to sum identities that we just looked at. If I were to write all of the rest of them up here, just so that you can see them, they are in your textbook, so this may be a bit redundant, but just so you can see them on the video. All of the sum to product identities, well, I'll leave this one up here. We usually write the sum on the left side, so we'd switch the sides here. So that's one of them. Another one is the sine of A minus the sine of B is equal to 2 times the cosine of A plus B over 2 times the sine of A minus B over 2. You're going to see a lot of similarities in these formulas. We also have the cosine of A plus the cosine of B equals 2 times the cosine of A plus B over 2 times the cosine of A minus B over 2. Again, similarities, but just a couple little tweaks that are different in each of these. And then finally, the cosine of A minus the cosine of B equals 2. Sorry, it doesn't equal 2. It equals negative 2 times the sine of A plus B over 2 times the sine of A minus B over 2. I think that's everything. I think I wrote those correctly. Did I redo them? No, that's all. Yeah, that's all 4 of them. Okay, so 4 sum to product identities. We say sum, but it could include a difference too, difference to product. But we call them all sums. All right, so we've established 4 more identities. This section is full of identities. We've got our 4 double angle, 5 double angle identities. We have our 4 product to sum identities, and now 4 sum to product identities, all established here. And we can use all of these identities to either evaluate trig functions or combinations of trig functions, or to prove other identities with them.